Hello, Mr. Bryant here with a video about torque. So torque is a word you may have heard before, but what we mean by it in physics is that it is the rotational analog to force. So just like forces cause linear acceleration in a straight line, torques cause angular acceleration. They cause things to speed up in a rotational manner. The symbol that we use for torque is the Greek letter tau, T-A-U, and it kind of looks like a one-legged pie. So if you draw a pie, but you draw one leg instead of two, that's a lowercase tau. Now torque depends on basically two things. It depends not only on the force that you apply, but also where and how you apply that force as it relates to the axis of rotation. So I've drawn a door here. It's sort of an overhead view of a door. So imagine being up in the sky looking down on a gate or a door. And the hinge is over here. We have the part of the door, and then there's two handles, like the handles of the classroom door that we have here from overhead. If we apply a force here in the middle of the door, we get a certain amount of torque. But if we apply that force a little farther from the axis of rotation, over here where the handle is, we get a lot more torque. That's in fact why we put the handle as far from the hinge as possible. It makes the door easier to angularly accelerate. It makes the door easier to open. So that's one rule. More torque the farther from the axis of rotation. The second thing is, even if we apply the force out here, far from the hinge, far from the axis, we also get more torque if we apply the force perpendicularly to the door at a 90-degree angle. We get less torque for the same force if we apply it at some angle other than 90 degrees. So more torque if the force is applied perpendicular to the door. So the next slide shows the equation that we use to calculate the magnitude of the torque. And it says torque equals R times F times the sine of phi. So tau there for torque. R is the distance from the axis to where the force is applied. F is for force. And the sine, of course, and the Greek letter phi, P-H-I, is the angle between R and F. So from the distance where you apply it from the hinge, the axis, to where the force is applied. So here's an example of that. Same example here with our hinged door, looking from overhead. If we apply a force like that at some angle, at this distance from the hinge, that makes this distance R. That makes our force here, and the angle between R and F is our phi. That's our angle there. The units for torque are meters times newtons, or newtons times meters, depending on how you would like to write it. But do be careful when you write that unit. If you are a little sloppy, it could look like you're writing millinewtons, as in 1,000th of a newton. So always be careful to put that little dot in there so that we know that these are two things multiplied together. Even better, I think, to write it this way, newtons times meters, and put the little dot in there so we know that that's the unit for torque and not something else. And then the last two slides are two examples, so make sure to put those examples in your notes. Example 1, Tyler pushes perpendicularly on a door with a force of 32 newtons at a distance of 0.72 meters from the hinge. Calculate the torque he applies. So I drew a door here, I drew the distance from the hinge to where he applied the force, which is 0.72 meters, and the force is 32 newtons. I even drew the angle as a right angle, 90 degrees there. So my torque equation is RF sine phi. R is 0.72 meters. F is 32 newtons. And we have the sine of 90 in this case. Do you remember that the sine of 90 is 1? So this turns out to be 0.72 times 32 times 1, which is 2304. And rounded off, we would write 23 newtons times meters. Now, I put a direction here on the end. It says counterclockwise, or CCW. So this door would tend to rotate in a direction counter to the hands on a clock. And so sometimes we write that as counterclockwise, or CCW. Example 2, maybe Vanessa comes along and pushes on a door, as in the diagram here. Calculate the torque she produces. So in this case, I had her apply the force 0.7 meters from the hinge. It's 35 newtons in this case. But the angle between R and F is a little bit bigger than 90. It's 120. And so in this case, we would write RF sine phi, where R is 0.7, F is 35, and we have the sine of 120. Now that turns out to be, I think, the square root of 3 over 2, or 0.86 something. Multiply by that, and then we get 21.217. Rounding that off to 2 sig figs, 21 newtons times meters. I'll put the dot there. And again, this is also counterclockwise. It would tend to rotate that door opposite the direction of a clock. So CCW there for that. Okay, thanks.